Ever pondered the importance of achieving high protein expression in your experiments? Surprisingly, many lab constructs involving protein expression fall short of optimal performance. Hello, I'm Alvaro from the Teselagen team. Today, I'll guide you through a simple yet effective method to enhance your protein yield using Teselagen tools. We're diving into a classic yet powerful technique, codon optimization. You might already be familiar with it, perhaps even incorporating it into your work regularly. But if you're not, fear not. We are here to introduce you to the Celagen's handy shortcuts for optimizing your native coding sequence tailored to your selected host. Let's unlock the full potential of your experiments together. Ready to dive in? Let's go. First, ensure you have your protein amino acid sequence ready. For today's tutorial, I've selected an actinobacterial protein for expression in E. coli. I'll copy directly its amino acid sequence from its UniProt file and seamlessly paste it into the Celagen's design module as a new amino acid sequence. You can easily upload your sequence from a FASTA or similar file. Just remember, for this codon optimization to work its charm, we are dealing with amino acid sequences. Ever noticed how the codon usage in your protein's native DNA sequence differs from what E. coli prefers? Manually optimizing each codon would be a time-consuming task. But fear not. Enter the Celagen's nifty trick, ready to work its magic in the blink of an eye. But hold on to your seat. It's quick, and you won't want to miss it. Let's delve into the procedural details. Firstly, carefully select the amino acids within your protein needing codon optimization. I'm focusing solely on the mature protein sequence, excluding the native signal peptide used for extracellular translocation. Now, onto the pivotal step. Right-click your selection to access the contextual menu and choose the Reverse Translate option. Select the target organism for tailored codon optimization in the ensuing dialog box. Whether you opt for a personalized codon map or a remote alternative is entirely up to you. For this demonstration, I'll stick with the E. coli high expression codon utilization table and the emboss back translation algorithm. After a brief wait, an announcement appears on your screen indicating the availability of a freshly generated back-translated sequence. A simple click thereafter grants access to your pristine codon-optimized DNA sequence. Simple, yet effective. What if you only have your protein's DNA sequence and not its amino acid sequence? No need to fret. The same procedure can be seamlessly executed starting from a DNA sequence already in your Teselagen library. Let me demonstrate how. Firstly, in my DNA sequence library, I will double-click on the DNA sequence of the required open reading frame. From there, I will select the section I aim to optimize for E. coli's codon usage. Like before, for this example, I will exclude the signal peptide from the native sequence and only retain the sequence of my mature protein. Then, a simple right-click on the selected sequence will reveal a contextual menu where I can copy the translated protein sequence and create a new amino acid sequence to proceed to the next steps. An even simpler and faster alternative is to create a new translation of the selected sequence, double-click again on the selection, and choose the Reverse Translate option from the contextual menu. From there, we can choose the codon optimization table and algorithm and continue as we did before. Now, let's explore the alterations in DNA bases introduced to our sequence to optimize codon usage and protein expression in E. coli. To do this, we will align our optimized DNA sequence with the original sequence of the protein in its native actinobacterial organism. First, I will select the entire DNA sequence and access the alignment tool in the toolbar. In the ensuing window, I will opt for the pairwise alignment feature. proceed to the next page and select a sequence from my DNA sequence library. Fortunately, I've already downloaded the native DNA sequence of the gene encoding my protein from GenBank into the TeSelaGen platform. After clicking Continue, I'm directed into the Alignment section under the Data tab. Once the alignment task is complete, I click on the task to access the alignment itself. We can see how my codon-optimized sequence aligns with the open reading frame in the original gene sequence. You will notice sections highlighted in red, indicating the alterations introduced by the TeSelaGen's codon optimization algorithm. As we scroll to the right, the entirety of the alignment unfolds before us. In my example, over 200 bases have been strategically replaced to harmonize codon usage for optimal protein expression. This simple yet powerful trick ensures we kick off our recombinant expression experiments on the right foot, aiming for maximum protein expression. It's a game changer you won't want to overlook. Now, you might be wondering, we've got this highly optimized open reading frame sequence, but how do we actually construct and insert it into a suitable E. coli expression vector? Excellent question. That's precisely what we'll cover in our upcoming tutorial videos. Stay tuned to become a true expert in leveraging TeSelaGen's tools to streamline your lab protocols. This video is part of our protein engineering tutorial series designed to help you optimize your experiments. Be sure to explore our other videos for more valuable tips. See you next time.